What's up? Oh yeah, we'll do that in a minute. Sure. Yeah. But you have to be in your full. Hey. Shh. Hey, just FYI, to be counted, you must be in full mass uniform.
When are they counting?
Right? 7th hour. So that means you need, if you're a gentleman, you need a sweater and a tie and a lanyard. Sweater and a tie and a lanyard.
Your sweater looks better on you than it does.
Ladies, you need sweater, blouse.
I don't even have a green socks.
No. It says Colin Whalen.
I think that sweater counts. I think you're in.
It's just different font. This is Glacios. I don't think this is Whalen. Who is Glacios? I don't think this is good. Who the hell is Glacios? Oh, these are green, my friend. Those are not green. I see green on all the sides. You just drew on your There's green boxes on.
All right, here. Let's get this out of the way. On with the show. You got to do better. Today, we're going to talk about graphing rational functions. Shh. When we talk about a rational function, rational functions are of the form P of x over Q of x, where P of x and Q of x are polynomials. Our main focus today is going to be on graphing, but before we talk about graphing, let's talk about domains, because will be being able to determine the domain will be helpful when graphing. So we talked about how to find domains algebraically in first semester. Does anybody remember how to do this? Well, let's ask you the question here. If I look at my function here, what operations are going on in x plus 4 over 2x minus 1? What operations? Great. Add, addition, and subtraction. What else? Okay, and what else? Division. Great. Of those 4 operations, which one can cause something to be or can get an undefined answer?
Division?
Only division. When does division create an undefined answer? You do, you just don't remember.
I just don't.
When you divide by?
1.
No, dividing by 1 is definitely okay.
0.
0. So, to find the domain for our function, the only thing that matters is the division. And the only thing that matters with division is not dividing by 0. So I'm just going to take the denominator and set it not equal to 0. So when I solve, I get x cannot equal 1/2. So to write the interval now for the domain, I go negative infinity up to 1/2, union 1/2, up to positive infinity. Notice I'm using parentheses here rather than brackets because the parentheses indicate that that value is not included in the set. So this interval that I wrote here contains all the real numbers except for 1/2. Everybody's cool? Hopefully we kind of remember doing this. Let's try another. Okay. If I want the domain of this rational function, what do I have to worry about? The denominator can't be 0. So far, so good. Okay. To solve this, what do I have to do? It's not a linear equation like the previous one. I have to do something different here. What should I do to solve this? Any ideas? X cubed minus 4x not equal to 0. Did you notice something in common with each term? It's going to be painful if nobody wants to try to help. I'm going to start calling on people, unless I have some volunteers. What would I want to do to try to start solving this? X cubed minus 4x not equal to 0. Great, Reagan. We'll start by factoring out an x, because we notice that there's a greatest common factor of x in each term. If we look at the remaining piece, the x squared minus 4, what do you notice about that?
Can you take another x out?
I can't take another x out of x squared minus 4. Right. But x squared minus 4 should look familiar. X squared minus 4. What can I do to that? Starts with an F.
Factor.
Yeah, how does it factor?
Oh, 2 and 2.
X minus 2,
X plus 2.
x plus 2. That's great. Teamwork made the dream work there, right? Now that they are completely factored, we can set each piece not equal to 0. So there's one answer, 2 answer, and 3 answer. Everybody feels good? So what we're saying is that x can be any real number except for 0, 2, and negative 2. So I want to construct this, write this now as an interval notation. So I'll go negative infinity to which number?
9.
Negative infinity to what number?
Oh, 2.
No.
0.
No. No.
Negative 2.
Negative 2. Why does it have to?
I said 2, and you said 2 too.
Nobody's in ballet class. There's no tutus here. Ha! Why did it have to be negative 2 first?
Because negative 2.
Because it comes first on the number line, right?
Yep.
I start with the smallest one. Okay, and then we'll go negative 2 to what value? Now where? Nope.
0.
0. Why 0 next? Why 0 next?
Then, it comes before.
Because it's the next smallest one remaining, right?
Then it's 2.
And then we'll go 0 to,
2.
great. And then we end with,
There's more. 2.
Yeah, 2 to positive infinity. Good job. Teamwork. Okay, that's like the hardest it gets for domains, right? Not brutal. Should be within our comfort zone. All right. The main thing, though, that we want to talk about today is graphing. And to graph these rational functions, we're not going to really going to make a table of points because, well, it could be a lot of points that you need to get a decent picture of what's going on. Instead, what we're going to do is start by collecting key features. So the first kind of key feature we're going to collect is the discontinuities. So there's 2 types. We have a vertical asymptote So to find the vertical asymptotes, we're going to set our reduced denominator equal to 0 and then solve. The other discontinuity we may have is called a removable discontinuity. To find the removable discontinuity, we're going to set the factors completely reduced from the denominator equal to 0 and solve. Okay, let's do a quick example here. Okay. So let's say our rational function is x squared plus 3x plus 2 over x squared minus 2x minus 3. Notice to find any of the discontinuities, we need to look at the reduced problem. In order to reduce a rational function, what do we have to do? To reduce a rational expression, what do we have to do? Give you a hint. Starts with an F.
Factor.
Factor. Great. How does x squared plus 3x plus 2 factor? Has to multiply to 2. Great. Thank you, Reagan. Again, we have to multiply to get 2 and add to get 3. How about the denominator? X squared minus 2x minus 3.
It's the same thing. 1.
X minus 3.
There you go. What do you notice when you look at the reduced form? Or the factored form, excuse me. Look at the factored form. What can we do? It's our...
Set it equal to 0.
No, we're not doing... What? If we FOIL, we're back to where we started. Look at the factors. What are the same? So the x's aren't factors. A factor is a thing in the parenthesis. Is there a factor that's the same?
The 1s are the same.
The x plus 1s, right? So because there's 1 on top and 1 on bottom, we can reduce those out. So what is our reduced answer? Okay. So our vertical asymptotes call for the reduced denominator set equal to 0 and solve. Boom. Everybody cool with that? Our removable discontinuity calls for the factors that are completely reduced from the denominator. Are there any x plus 1s left after I cross that out? Nope. So that makes it a removable discontinuity at -1. But a removable discontinuity isn't a line, a vertical line like a vertical asymptote is. It's a point. How do I find the y coordinate for that point? I'll give you a hint. Where did I get that from? What, Mr. Kulik, did you just plug in? Look at what I did. To find the y coordinate for the removal discontinuity, I just plugged my x into the reduced fraction. And because the x plus 1 factors are gone, I don't get a 0 in the denominator anymore. I just get a number. So that point there is the location of my removable discontinuity. How do we feel so far? Question. Does every rational function have a vertical asymptote? No, they don't need to. For example, if I have 1 over x squared plus 1, the denominator x squared plus 1 isn't factorable. And if you set it equal to 0 and solve, you get an imaginary solution. So you certainly don't need to have a vertical asymptote. Are you always going to get a removable discontinuity? Well, no, definitely not. I mean, if we go back and look at like this example right here, that has no removable discontinuity. There's nothing to factor. Nothing crosses out, so I can't get a removable discontinuity there. Next question, could I get more than one vertical asymptote? What do you think? Definitely, right? If the same problem, if the numerator was just 1, then when I set, there's nothing to reduce, so I set the denominator equal to 0. There's 2 factors, I'll get 2 vertical asymptotes. Could I get 2 removable discontinuities? Definitely. I'm not going to do it a problem like that because it's a kind of a real royal hassle. Here's the biggest question, though. Is it possible to reduce the fraction and not get a removable discontinuity? Let me show you an example. So first step is to, starts with an F, factor it all. How does the numerator factor? Or the denominator? Just somebody tell me one of them, please, for the love of God. Numerator, denominator. Somebody tell me one of them. How does they factor? X plus 1 for the numerator, right? Great. X plus 1, x minus 1 in the numerator. How about the denominator? X plus 1 and x plus 1, right? So the x plus 1s can cancel out. But notice, I still have an x plus 1 in the denominator, right? Did I completely reduce the x plus 1s from the denominator? No. What does that mean? Means the x plus 1 that's left is a vertical asymptote. But because I still have x plus 1s left, even though I crossed them out, there is no removable discontinuity. How do you guys feel on this? Is this okay? All right. The next key feature we're going to look at are the end behavior asymptotes. And there's 3 cases here. All 3 cases for these end behavior asymptotes are going to be dictated by the degree of the numerator and the degree of the denominator. Just do the slider. No, they should do it. I'm going to do it now. All right. So our first criteria says if the degree of the numerator is less than the degree of the denominator, then the end behavior asymptote is y equals 0. What's the degree of the numerator in this example? What's the numerator? 1. What's the degree of the polynomial f of x equals 1? Are there any x's? So the degree should be 0. What's the degree of the denominator? 2. Degree of the numerator is less than the degree of the denominator, so my end behavior asymptote is y equals 0. Okay, didn't take much to do that, right? We just had to look at the degrees. There's not even really anything to calculate. I like it. That's pretty easy, Mr. Kulik. If the degree of the numerator equals the degree of the denominator, then our end behavior asymptote is y equals a sub n over b sub n, where a sub n is the leading coefficient of the numerator and b sub n is the leading coefficient of the denominator. Okay, so let's take a look here. 2x plus 5 over 5 minus x. What's the degree of the numerator? Who can tell me? Degree of the numerator. Two x plus 5. What is the degree of that polynomial? The biggest power of x is? You don't know the biggest power of x for 2x plus 5? It's 1! It's x to the first. It's there, but we don't write it. What's the degree of the denominator? 1! They're equal. So what should my end behavior asymptote be? Y equals. What's the leading coefficient of the numerator? Leading coefficient of the numerator is 2. Very good. What's the leading coefficient of the denominator? Not 5. Not 1. Not x. Not 0. Minus 1. Why is it minus 1? There's a 1 in front of the x, and there's a subtraction symbol in front of it, right? You may. So y equals -2 should be our end behavior asymptote there. The third, if the degree of the numerator is greater than the degree of the denominator, then our end behavior asymptote is y equals the quotient of P of x, our numerator, divided by Q of x, our denominator. All right. What's the degree of the numerator? For x squared plus 5x plus 7. Thank you. Degree of the denominator is 1. So the degree of the numerator is greater than the degree of the denominator. It says then I need to do the quotient. I need to find the quotient of x squared plus 5x plus 7 divided by x plus 3. How do you want to do that polynomial division? What are the two ways I have to do polynomial division? Yes. Long division or? Great. Which one should I use in this case? How do you know I can use synthetic division? So degree 1 and leading coefficient 1. Very good. Yes. Like that. So I'll do my little setup. So this is the only piece I care about. Everybody okay? All right. The third key feature we're going to worry about then are the zeros. To find the zeros, we set the reduced numerator equal to 0 and solve. And the last thing we're going to want is the y-intercept. It just plug 0 in for x and then evaluate. All right, it's example time. Let's draw some graphs using key features. All right, first thing I want to do is to factor my rational expression to see if there's any reducing I can do, because everything requires a reduced thingamajigger. Lucas, will you grab that door for me when you have a sec? So obviously x minus 1, no reducing to do there. X squared minus 4, though, how does that reduce? Or how does that factor? X squared minus 4. We did it already, guys. We did it today. Sure. X squared minus 4. Dude, it's x plus 2x minus 2. You gotta be good at factoring these things. These quadratics are gonna happen all the time this chapter. Anything to reduce? Nope. So I'll just take my denominator, set each piece equal to 0. Each of those will be vertical asymptotes. Because there was no reducing to do, I know there's no removable discontinuity. For my end behavior asymptotes, the degree of the numerator is degree of x minus 1 is it is 1, and the degree of the denominator is 2. Since the degree of the numerator is less than the degree of the denominator, we know that that end behavior asymptote is y equals 0. For the zeros, we just take the numerator, set it equal to 0. I always write my zeros as a point so I don't get confused and think it's a vertical asymptote. And then my last one is my y-intercept. So that's going to be, I know the x-coordinate is always 0. The y is going to be 0 minus 1 over 0 squared minus 4. So that's 1/4. So 0, 1/4. So far, so good? All right. Let's draw ourselves a graph. I'm going to go by like half units. So I'm going to start by drawing in my asymptotes. So far, so good. I'm going to draw the point 1, 0, and then the point 0, 1/4. So now I've plotted all my key features onto this graph, right? Okay. So the first piece I need to know, because I know my graph isn't going to cross the asymptotes. Yes, I know that the left end of my graph is going to look like one of those two things. I don't know which one of those two quite yet, but I know it's going to look like one of those two things. Is that okay? Because I know it's got to follow the asymptotes, but not cross them. So what I'm going to do is I'm going to just pick a test value, say like -3, and I'm going to come back here and plug in and see if I get a positive or a negative value. So -3 minus 1 is negative. -3 plus 2 is negative. And then -3 minus 2 is negative. So I have negative over negative times negative, which is negative over positive, which is just a negative. Is everybody okay with what I did there? What does that tell me? I want the piece with the negative y coordinate. Everybody's okay with that? Now here, I know that my graph has to look like that. Part of my graph has to look like that. Because again, I can't cross the asymptote, so I couldn't start down here and cross because I found all the zeros, so I can't have that crossing. Everybody's okay with that reasoning? But I do need to figure out whether this last piece goes like that or like that. What am I going to do? Well, I'm going to pick a test value, say like positive 1.5, and see if I get a positive or negative value. So if I plug in 1.5, I get positive on top, positive times negative. So positive over negative is negative. So that guy must look like that. And then my last Chekaruski is here. I know that it's going to look like one of those two things. To check, I'm just going to pick a value for x over here, say like positive 3. If I plug positive 3 and I get positive over positive times positive, that's all positive. So I know I want the piece that's above the x-axis. And there I go. What do you guys think? Let's do another, eh? Okay. First thing I want to do, check to see if I can reduce this thing. Look at the polynomials though. Can I reduce this? No, how can I tell? They're all degree 1 polynomials with leading coefficients of plus or minus 1, right? Like nothing to really do here. So we'll just dive right in. Vertical asymptotes, denominator set equal to 0. Because I could do no reducing, I know there is no removal discontinuity. The end behaviored asymptotes, the degree for the numerator equals the degree for the denominator, because what are their degrees both? What are both the degrees? 1. Yeah, 1. So I know that my asymptote is leading coefficient of the numerator over leading coefficient of the denominator, or just -1. It's 25 minutes till lunch. I don't know why the Quasimodo's ringing the church bells here, but this class ends at 12:25.
It's 12:25.
I'm sorry, 12:50. Lunch ended at 12:25. So far, so good? Now we'll find our zeros. That's the numerator set equal to 0. And again, I like to write those as ordered pairs so I don't confuse myself and accidentally draw them as an asymptote. And then I need my y-intercept. X is always 0. And then y is just, well, I'm plugging 0 in, so I have 2/3. So I have 0, 2/3. So far, so good? Everybody feel like it was okay finding those key points? All right, let's draw a graph then. Again, I'm going to go by halves here. So 1, 2, 3, 4, 5, 6. There's 2, 0. There's like 0, 2/3. Okay. So if I look over here, I don't know whether I'm going to be doing this or this at first glance, right? But I really do. Because this would be a 0. Correct? How many zeros do I have? Just 1. I found it already. Is it that spot right there? It is not. So I know that that's not my, can't be my graph. It has to be down there. Everybody's okay? My other piece, well, it's got to connect through those points, can't cross the asymptotes. It's got to look like that. And I'm done. I didn't even have to do any test values on that one. Yes. That's a good deal. Everybody okay with what I did there? The asymptotes can help us enormously. Last example for today. and then we can stop. I know, Mr. Kulik, it feels like we barely got started. It does feel that way sometimes, doesn't it? All right. So I'll start by checking to see if I can do any reducing. I notice the numerator does factor. But no reducing can occur, so whatever. What are you guys starting to think about the appearance of these removable discontinuities? Is that going to happen frequently? Doesn't seem like it, right? We've yet to see one in any of the examples I had planned for you. What's the degree for the numerator? It's 2. What's the degree for the denominator? 1. Uh-oh, that's the polynomial division situation, but fortunately, it's not too bad because it's a synthetic division situation. Boy, howdy, I like that. Makes life quite a bit easier. The zeros, we're going to take the, just say the factors from the numerator and set them equal to 0. And the last is I want that y-intercept. I know I always pick x to be 0. And then my y is how we feeling here? So far, so good? Okay. So again, I'm going to go by halves. So 1, 2, 3, 4. Okay. To graph y equals -6. What is the graph of y equals negative, or y equals x minus 6? What's that graph look like? It's a line, my dudes. How many points do we need to graph a line? 2. I'm going to pick x to be 0. So 1 point is 0, -6. I'll pick the other point to be 6, which gives me the point 6, 0. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. And let's see, I have 0, negative, or -1, 0. Then I have 5, 0. and then 0, 2.5, so it's 1, 2, half. So right away, I can see that that part of my graph has to look like that, right? Everybody's okay? The only way I can connect those 3 points and not go through the asymptotes is to do that. What I don't know right away, and then I'm left with choosing either this one or this one. I can tell which one I want without having to do anything else. Which one do I want? The upper one or the lower one? I want the lower one because the upper one has to cross the x-axis, but I already found all the zeros, all the x-intercepts. I found them already. There's not another one over here. So I know it can't be that one. So that's what my graph has to look like. Is everybody okay with how I did that? Time for you guys to do some practice. Let's look here. You guys should be able to do 1 through 8, and then 13 to 24. Okie dokie, artichokes. Questions? I'm going to stop talking then. Okay. You guys have approximately 15